Alrighty, I'm gonna attempt to teach y'all a little bit how to use Half-Life applications. Now, why would you use Half-Life applications? Because if you're a mad scientist, you know, you have to do experiments with these unstable, radioactive, crazy elements, right? And then, these elements have a half-life, right? Like all the ones down here that you can see. So, what do we, what does that mean? It means that, that every certain period of time, the amount of this compound of a certain element diminishes by half. So half of it's gone. Say the half-life is a year, then half of that element, half of the compound is going to be gone in a year, right? And some elements have extremely short half-lives, like 60 milliseconds, for example. So let's do a calculation to see how long would it take. How many days would it take for 5 ounces of californium to diminish to 0.02 ounces or less? So californium has a half-life of roughly, depending on the isotope, 180 days more or less. This is how we set up our half-life type problem. Put the original, the initial amount here, and we know that our initial amount is 5 ounces. Then multiply here by the rate, which is 0.5, because this is half-life. If it were something different, it could be more or less than 0.5. And then up here, we're going to put an exponent, the time. And so you just put the number of units. The units could be years, seconds, etc. So for the application of half-lives, we're only going to, our unit will be half-lives, as opposed to plain Jane years or days or months or seconds. So even if your half-life is 180 days long, you'll just use 1 to represent those 180 days. Because if you put in 180 with this rate of 0.5, then that would be like 180 half-lives. You have to think about it a little bit, but if you don't understand, that's fine. Just keep going. Now, let's plug in the numbers from our problem. So the original amount is 5 ounces. So 5 times the rate is 0.5, because it's half-life, not compound interest. Because you know, if you're using this kind of equation to calculate compound interest, or your taxes or other things, the number won't necessarily be 0.5. But our rate is 0.5 because this is half-life. And the exponent here, the time, is going to be, let's try out, how about 5 half-lives? Okay, we can see 5 half-lives is still too few. Now, if we try 10 half-lives, that's too much. 8 half-lives is the lucky number, because it's just below 0.02 ounces, and we want a 0.02 less. So that's our number right there. 8 times 180, that gives us the total number of days that it'll take the californium to diminish to 0.02 ounces, which is 1,440 days approximately, in case you're wondering. Now, let's try with a different kind of element. How about livermorium, which used to be known as ununhexium, but then they changed the name. In 7 years, what will remain of 20 pounds of livermorium? This problem is different because instead of trying to figure out how long it will take to get down to a certain amount, we're going to figure out what amount it'll get down to after a certain amount of time. So here we don't have to do the guessing and testing that we did with the last problem. So this one's actually easier. All we got to do is take the original amount, which is 20 pounds, times 0.5, our rate, because it's a half-life and not something else, the rate 0.5, with the exponent of our time, which is 7 years. Now let's assume the half-life of this isotope of livermorium is 20 days. And 20 days, it decreases by half. Even though the longest half-life of any isotope of livermorium is about 60 milliseconds. But let's go with 20 days. Now, 7 years, help us get to that point. 7 years times 365 equals 2,555. And now let's divide that by 20. That gives us 127.75. That'll be how many half-lives we're calculating here. So 20 pounds times 0.5 to the power of 127.75 gives us precisely 6.9895323 times 10 to the power of negative 38. Wow, that's a pretty small number right there. So there's like 38 zeros after the decimal before the 698 starts. That's a pretty small amount right there. Very small amount, actually. Like, so small you can't even see it. Anyhow, hopefully that helped y'all. I'm going to do my final chow.